In this next video, we're going to take a look at measurement units for radiation. And there are two main methods for measuring radiation, so let's go through them. All right, and the first one is just simply looking at radiation as a physical unit. All right, and let's take a look at what this means. Basically, it means that we're going to do a physical measure of decay activity. All right, and usually the way that it's done is the number of nuclei that decay per unit time. All right, so for example, if you're a chemist studying nuclear decay, you might use one of these physical properties just because, it makes a lot of sense. However, if you're looking at harm, you would go with the second technique, which is biological. All right, so the biological methods are looking at the damage caused. All right, so very, very different intents and purposes with each of these. All right, and another cool thing with the biological one is that it accounts for the fact that not all radiation types are equal, right? So let's write that down. So it accounts for the fact that not all radiation types are equal. We saw in one of our previous videos that, for example, alpha particles can be stopped essentially by a piece of paper. Beta particles will travel further through air, and then gamma rays, if they're penetrating, can go very, very far. In some cases, we need feet of lead between us and the source to prevent us from being exposed to harmful gamma rays. All right, so let's kind of go through the list of each of these, and I'm just going to start off with physical. And then after we're done with this, we'll take a look at the biological ones. All right, so the first one we're going to look at is Curie. And this is named after the chemist Marie Curie, who worked on this a lot in the early 1900s along with her husband. And she actually won 2 Nobel Prizes, pretty fascinating. But when she was initially studying radiation, it was a brand new concept, right? Unfortunately, a lot of the people that worked in her lab were exposed to a tremendous amount of radiation. But a Curie is a unit with the symbol Ci, and what it is it's 3.7 times 10 to the 10th nuclear disintegrations per second. All right, so the problem with this is that this is a huge amount of decay, right? So quite often what you do is you measure it in millicurie or picocurie. These smaller units are a lot more manageable when chemists are working with them because very rarely would you ever encounter a situation where you're exposed to, mini curie. All right, and there's been a newer one that's tried to be pushed in the United States, but it hasn't really caught on, but we still want to present it because you might run into it. And I'm going to butcher this because it's a French name, but I think it's becquerel, and the symbol for this unit is BQ. And this one's a lot more manageable. Like I said, a curie is a massive amount. 1 curie of exposure is a ton of radiation, where this one is just 1 nuclear disintegration per second. So it's a lot more manageable as a unit. Okay, so those are the two main ones, and quite obviously we can relate these to one another too, because they're looking at the number of nuclei that decay per second. It's just got a different constant for each of those. Okay, now let's take a look at the biological ones. Like I said, the biological ones are typically used when you're studying the damage caused by radiation, right? Or in this case, trying to measure exposure to analyze or assess risk. Okay, so the first one is Roentgen, and its symbol is R. Okay, so it's a capital R, and this one is used with X-rays and gamma rays. Oops. All right, so it's not going to really assess alpha particles or beta particles like we saw before. X-rays and gamma rays, they don't really have a mass associated with them. They're just pure electromagnetic radiation. All right, and essentially what it is it can be defined as the amount of radiation that generates. And I'm going to put a list here, or sorry, two different lines here, because there's two different ways of measuring this. The first one is 2.1 times 10 to the 9th ion pairs in 1 cubic centimeter of air. Right? So if you're measuring it in air, this would be the value you would use. However, if you're dealing with something that's not in air, like a solid, you would use a different value. And specifically, you would use 1.8 times 10 to the 12th ion pairs in tissue. Or I should say 1 gram of tissue, excuse me. All right, so like I said, this is used to really investigate the risk or damage caused by radiation exposure. Okay, we've got a few more. So the next one is just called rad. And the symbol for this is capital D. And 1 rad transfers 1.0 times 10 to the negative second joules. But remember, joules and calories are related, so we could express this in calories. And if you express it in calories, it's 2.4 times 10 to the negative 3 calories of energy to 1 kilogram of tissue. So the main difference between these two, right, is the first one looks at ion pairs being formed, right? And you might be wondering, well, what does this even mean? Well, if you're exposed to an X-ray or gamma ray, you can actually ionize a neutral molecule and form a cation and anion pair, right? So basically separate it apart by breaking covalent bonds. Where down here, it's just saying, all right, what's the amount of energy being transferred into the tissue? And it's completely ignoring these ion pairs. All right, let's do the next one. The next one's a little bit different. It's a gray, and the symbol is GY. But this is the cousin of the rad, all right? And it says 1 gray as a unit of radiation transfers 1.0 joules of energy to 1 kilogram of tissue. All right, so you can see that these are closely related. In fact, we can convert between these very easily. All right, one interesting thing with this, right, is these two down here, they don't talk about the type of radiation. Up here, we said that it involves gamma rays, right? So these last two are, they don't account for which radiation type we're being exposed to. Are we being exposed to alpha, beta, or gamma? So let's just make a note here. So this does not account for type of radiation. So it is a little bit limiting in that regard, but depending on the field that you're in, you may use one of these. And then the last one is, I think, the most interesting one. It's REM. And basically, REM deals with the problem that we just described here, where these top two don't account for the type of radiation, where REM is a little bit more broad. And it says that 1 REM of any type of radiation is equal to 1 Rontgen of X-rays. And it's important to note that this could be additive. So let's say we have a radioactive decay where you're emitting both beta particles and gamma rays, right? This would say, well, let's add those both up together and calculate the net effect of them and try to find the damage that they cause equivalent to the Rontgen, right? So it's a bit different that way. And I just wanted to go over all of these. I know this is a lot to remember. I just wanted to introduce all of these because depending on the field that you go into, you'll probably have one that you may refer to. So let's take a look at the chart in our book. And this kind of takes a look at all of these along with their relationships between units, right? So the first two we talked about were the physical ones, where we were looking at the number of nuclei that decay per second. But we said that they're related, so we can actually convert between these using the conversion factors shown on the right. And then on the bottom, these were the biological ones. And we can convert between some of these, specifically these middle two, the rad and gray, are really easy to remember. And then rem, we said is 1 rem is equal to the additive, or all radiation added together that's equivalent to an X-ray. So those are the main units that you might run into. The tricky thing, though, is how do we detect radiation either in a hospital or in some other setting? So let's talk about that next. So detection of radiation. And we're going to go over the 3 main types. So the first one that's really common is a film badge. All right. One of the interesting stories I heard was the first people that knew about the Trinity test, where we tested the first atomic bomb in the United States, the first people that knew that were civilians were actually, excuse me, some people developing film quite a few miles away. And the reason they knew was all their film went bad. And that was because of the radiation exposure. So when we were testing the first atomic bomb, we had a pretty naive understanding of the health impacts of radiation. And unfortunately, a number of people were exposed. But what this does is it shows qualitative exposure. But isn't very precise, right? So this might be good in a healthcare setting where you've got this badge that you have on your jacket, and if it gets completely exposed, you're like, oh shoot, I got exposed to something that I shouldn't have been exposed to. Or if it gets half exposed, you could say, I'm getting close to my limit. But it doesn't necessarily tell you a whole lot quantitatively, but it is useful as a cheap indicator in a healthcare setting. All right, the next one's pretty interesting. This is a scintillation counter. All right, and this one's pretty interesting in that the radiation will hit a phosphor surface. And emit a flash. Whoops. All right, and you might be wondering, well, what in the heck is a phosphor surface? Well, it's kind of interesting. There's this special phenomenon in chemistry where if you excite certain types of molecules, they undergo this process called phosphorescence. Basically meaning you could excite them maybe with a high energy laser, and then when you stop the laser, that surface will continue to glow for a while as it releases the energy back out. In this case, instead of using a laser to excite the surface, we're going to use radiation. And as it relaxes back down, it'll release energy back at you in the form of light, in this case, a flash. So in this case, you can say flashes per time. As an amount of radiation. right? So if you're getting a ton of flashes, that means you're being exposed to a lot of radiation. If you're getting only a handful of flashes, that means you're not being exposed to very much. All right, and then the last one is the one you're probably most familiar with, maybe hearing it on TV, but it's a Geiger counter. Specifically, it's called a Geiger-Müller tube. All right, and this one is the one that you've probably heard of if you even watched that Chernobyl series that I talked about. It's actually the background music, or it's in the background music there. It's that weird clicking noise that sounds really ominous. But what happens here is the radiation will ionize a gas inside a tube. So radiation ionizes low pressure gas. And the ions formed, can be counted. By a counter. All right, so every time it hits that detector, you might get that click noise. Let's take a look at what goes on inside this device, though, because I think it's interesting. Granted, I'm a chemist, so I think most of this stuff is. But let's zoom in on this. So over on the left-hand side, the path of radiation is going in this way, right? So it'll go through this little window here in our Geiger counter, and it will hit the gas on the inside. And like I said, this is low pressure gas. But when it does that, it will ionize some of the gas. The reason it's low pressure gas is we don't want the count rate to be way too high. So we want to minimize the number of gas molecules on the inside that can be ionized. So that's why it's low pressure. But anyways, when we form ions, it can be attracted to either this negative or positive part of the Geiger counter. And when it does this, we can actually detect the number of ions formed. So it'll go out to a counter circuit. So this is one of the main ways, at least commercially, that chemists or even health safety officials will go out and try to detect environmental radiation. All right, I know this was kind of a crash course, a lot to remember, but like I said, I just wanted to present all of these because I'm not really sure which field a lot of people will end up landing in. So I wanted to have a broad overview of the units you might encounter in your various professions. All right, I hope that helps, but let me know if you have any questions.